Hey, this is OXDF. And at the beginning of September, I actually stopped working for Hack the Box to pursue another opportunity that was really exciting. But as a goodbye present, the content team made me a personalized CTF with 4 challenges. What an awesome present. So you can't play this CTF, it's just for me, but I'm making videos for them anyway because I think they're interesting and you can still learn a lot. This challenge is Uncheesable. It's a hard forensics challenge and it's a memory dump. And it's from Canopus, who is not only a content engineer on the CTF and forensics challenges side of things, but also works really closely with the Volatility folks. Is just a memory forensics expert, fantastic CTF player as well. And the backstory is that I really pushed him to share his knowledge and put out a blog post that is now up on the Hack the Box website, showing how to create symbols for custom and just for Linux images in general. And so turnabout is fair play. He's throwing back at me now a hard forensics challenge. Let's go take a look. All right, we're in the CTF platform. Let's take a look at the challenge, Uncheesable. Oh no, we're dealing with a custom compiled Linux kernel. Shrug. If only there was a blog post about creating volatility symbols. The challenge is appropriately named Uncheesable because, well, you need to cheese it. Can't be cheesed if that's the way to go. This was an experiment turned challenge. I apologize for the difficulty and I hope you enjoy it. I did enjoy it. Thank you so much to Canopus for making this. It was very challenging and I had to check in a couple times to get direction. Yeah, it's fun. I learned a lot. I hope you will too watching this video. I've got the blog post here that Canopus wrote for Hack the Box. It goes into a ton of detail about volatility versus 2 versus 3, how it works, what layers are, memory mapping, symbols tables, creating symbols tables, why symbols tables are important to be able to run volatility. They're based, I'm gonna let you should go read this. This is great background. It's got a couple different approaches to creating symbols tables, but they all involve identifying the OS, going out to, if it's Ubuntu, go getting a copy of the debug symbols for that kernel, and then using that. And until we get to the very end, this somewhat automated procedure, nope, not this one. Let's see, experimental. Let's see, an experimental route. Here's the section. This section says, as you've probably noticed, hunting down the correct kernel version and hoping there's a debug package available is somewhat cumbersome. Enter BTF type format. It's a section on the kernel binary which contains information. Here's a blog post that explains how it can be used in conjunction with the System.map file to create an ISF symbols without downloading the debug kernel, just from the memory dump. That's exactly what we need. However, this entails we extract the bzImage file and the System.map from the memory dump, something that greatly diverges from the scope of this post and also requires manual work. And that's what we're going to have to do in this challenge. I will show, when we do dive in, we'll show that this is a custom kernel, but the challenge told us that. So we're going to have to proceed that way. And then the rest of this example proceeds to say, pretend we got that stuff somehow. They just downloaded it. Let's continue and show how to use it. And so it involves this BTF to JSON package. We will come back to that because we will eventually get a VM Linux bzImage as well as a System.map and banners, and we can use that to generate this. So that is that's the path we're going to go. Let's go ahead and dive in. All right, so the file I'm given is just a single mem.elf. If I do file on that, it's a LSB core file. That's a memory dump for Linux. And that's about all I got. Let's see, we can do LH on this. It's 273 megs. Not huge, but not small. And so the first question I have is, can I get one of these VM limbs bzImage files out of there? And so in doing some research, I kind of came across this thing talking about the boot sector, and this is the real mode kernel header. So this is the kernel header, and it's at an offset. It's got offsets. It's about 0.1f into it. And if you come down right here, I found some Stack Overflow posts that kind of pointed me this direction. Let's see, where there's a magic signature HDRS. And so the first thing I was like, oh, let's just do a grep HDRS mem.this. It matches. I mean, that's good. It's there. We can verify. I'm not sure how helpful that is. Let's do XXD on this. Less. We can do search for HDRS like this. If we look here, This is 4 bytes long. 2 bytes is jump instruction. So if we, let's see, this would be this right here. So this would be a jump instruction. Maybe, I don't know. We can check that out. And before that is AA55, which is right there. So that this is looking promising. So we can tell it's there. We can also say, let's see, if we put a O here, we can see it actually shows up 3 times. So it's kind of hard to say exactly which one. We will go find this a little bit more. We're gonna actually use Python. So let's do Python. Actually, sorry, I'm gonna do UV run Python 3.14. 3.14 has such a better REPL. So if you're gonna do Python, it's like boom. And this is the cool thing about UV is you just specify your Python version and bam, you're there. So let's check it out. Let's see. We're gonna do with open nem.elf. Now we're gonna read binary as f. I got used to the fact that it indents for you. It's quite nice. I just got used to it. Say data equals f.read, and boom, len data. There we go. We have our data. So we can do things like bytes hdrs in data. We can do data.index of hdrs. Cool. So the real thing. So the question is, I guess we can verify that. Let's see. So if we do data of this minus 4 colon this minus 2, there we should get that's 55 AA. Perfect. So we want them. So the next question would be where like this. Okay, this is an offset 202, and that's in hex clearly. So what is actually at the start of the thing? What should we expect? We expect actually this is kind of cool. I didn't know this going in, but I think I did know this in my head, but I didn't conceptualize it completely. So this minus OX 202, and then we'll just grab like 100. Not 100. We want this plus 100. There we go. This is an MZ file. How cool is that? It's actually MZ. You can see the PE header here. You think of MZs as Windows executables, but it's not. But it's kind of fudging, acting as a Windows executable so that the bootloader can handle it, and eventually then get it into this header down here. So I think you can even see here's the HDRS there. So we could loop over what it turns out. Let's see. Just one thing I lost some time on or played with for a while. So here's the index of that. If we grab this and do 67388 just to start one more, oops, we'll see that there's the next one. If we do the same thing with this, where we say, let's go back 202. Boom, boom. We don't have the MZ header here. So this is not actually, this is, I mean, yes, the header shows up. In fact, it is looking like these headers because here's the 55AA, but it's not the full image that I'm looking for. And so this is not one I want to pull. We could do the same thing here just by pulling, let's see, let's make this a 5. Get the next one. Probably a cleaner way to do this, but we're going this way. So we can do that and that. And also this one's not MZ. So this one's also not the boot image. And if we check one more, we come here. Oops, did not mean to do that. For you, data.index. There we go. We need to come here, grab this, make that a 7, and so there's only 3, all 3 of them, and only the first one is really a thing. I'm just gonna grab it. So what we're gonna do here is we're gonna say with open, and we're just gonna call it. We need something, so we'll say what do we call it? bzImage, and we'll write binary as f.write data colon that. And we just need to put in that first spot. So we'll scroll up here and find that. It's this one right here. Copy, paste like that, and I'm just going to write to the end of the file. Oops. I'll show you. This is so nice with 3.14. I can up arrow and get the whole block back. So a lot of times, if you've ever worked in a Python REPL before, and you have to you have a block, but you want to rerun it. And let's say it's got 10 lines, you have to up arrow to each line to get it. And anyway, this is very nice. So we're out of here. Let's get a file bzImage, and this is a Linux kernel boot executable. We have found it. Pretty cool. I like that. one thing I forgot to show you, and I'm going to show you now, is volatility. We can't do much with volatility until we have the symbols, but there's things we can do. So if we do I have installed volatility with UV tool install volatility 3 like this. You can also do with and then give it, there's a Yara X package and another package that are optional. This is in the documentation on the Volatility 3 page. But if you want to add those, you just put the with here. If you want to change your Python version, you can put Python 3.14 or whatever you want here. But that installs it such that when you do which vol or which vol shell, they are just available in your local bin. They're installed through virtual environments. UV is awesome. I got a blog post and a video on that. I'll post it. I'll link that as well. Yeah. So I got volatility. I can do volatility minus f mem.thing, and I can do banners.banner like that. I think it's banner. And we can see here, this is in fact a custom Linux thing. So Linux version 6693 from Canopus at Orion. This is why we have to dive in and do the finding our own bzImage. Cool. Okay, so now that we have that, there's a couple steps we need to do. First, we want to find the System.map. So there is a project here, let's see, called VM Linux to ELF that has two packages. We're going to use both VM Linux to ELF and CallSims Finder. So first, we're going to use CallSims Finder. I've installed this as well. This one has install instructions. Anytime you see pipx, UV tool. So I did UV tool install, and then this thing installs it perfectly for me. So now I can do CallSims. And we have CallSims Finder. We're just going to pass it this bzImage file. And if we just head for a second, we can see what comes out of it. Whoa, does not like being passed into head. Let's do this. Let's just run it. We'll get crazy. So it prints out some status stuff, and then this is the symbols.map. And it's literally just going through and dumping all these different function addresses and their addresses and what they are. And so what we really need to do is we need to pick this into System.map like that. Now, for this to get recognized by tools, I wish if I could tweak this a little bit, I would, but we're actually going to need to remove some of this header data. So like all this status stuff we don't need. It's not actually part of the file. We get rid of that. And now we have a System.map file. Now, to use this BTF to JSON file program, we're going to need the bzImage file in an ELF format. So this is where we use the VM Linux to ELF thing, bzImage, and I'm just going to call it bzImage.elf. And it seems to be finding the right things. It's doing the conversion, and I didn't remember it taking too long. But it might take a second. Let's see. I might pause the video if it takes longer than successfully wrote. And boom, if we do file on that, we have a Linux ELF executable, not stripped. That's what we need. So now I'll show you. This is the BFT to JSON file. This is actually a Rust program, but if you've got you're gonna want to install Cargo, like the Rust package manager, and then you can just install this using Rust. You'll have to clone this and then Cargo install it. Oh, there's also an executable. Okay, yeah, that's right. And there's even a precompiled. So you can get it off the release. I can't remember if I installed it with Rust or if I got it off the release, but I have it now. So we will run BTF to JSON. We're going to need to give it a couple things. We need to give it BTF, and that is going to be our bzImage.elf. We need to give it the map file, which is going to be System.map. We need to give it a banner. And the banner is going to be, how far back do I have to go? It might be worth running this again. We'll just run it again. Vol minus f mem.elf banners.banner that, and it will print. And we will grab you. I don't know why I'm grabbing the longer one. It feels better. Paste that in, and we can run this. It's going to print out a huge blob of JSON. I'm going to Control C that because it goes to my screen. I don't want it there. Let's see. We're going to call this Linux 6693.json. And we're going to write that there. If they get an error, that's fine. If we run a word count on this, it's one long line, a lot of characters. So the real test is, now we have the symbols file. Can we get Volatility to recognize it? I'm going to make a directory structure here. I'm going to call it symbols, and then it is Linux like that. Oops, make their piece, and then I'm going to move Linux there into symbols.linux like that. And now if I run vol -f mem.l, I can run -s and give it the symbols directory. And then I can say we'll do like linux.ps list.ps list. If we run this, we got the process list. And how cool is that? We now have custom symbols. Just to show you, if we were to try to do this without symbols, if we run this, it's just going to crash. And it's going to say, I can't find the stuff I need to go get in memory the thing to rebuild the process table. Okay, so we've got this process list we can take a look through. And most of this stuff is just standard Linux kernel system stuff. But right at the bottom, there's an SH process that's running an OXDF process. You see parent PID of 52, there's 52, so PID of 64 is OXDF. And that's clearly where we want to start looking, because like the rest of this all looks pretty standard. So there's a few ways we can look about this. One thing we can do is we can do vol-help and print all our stuff. And I like to just do grep Linux, and we get a thing here shows us the different. So we already did the banners. We can get the bash history. Might as well we can take a peek at that. Bash. Is that what it was? Linux.bash.bash. Ooh. See. Linux.bash.bash. Oh, I need symbols. I don't know why that's not there. I am -s and then symbols. Oh, there we go. Nothing interesting there. Go back up. We can get the elves in memory. That's kind of cool. Let's grab that and paste you. We can see that ox/bin/oxdf is in fact an elf that's there in memory. BusyBox we got working here. That's just so this is like probably like an Alpine environment or some kind of real small thing. Let's see. What else is interesting in here? Page cache files. We're gonna come back to that. We can get PS if we thought maybe there was like more arguments to our thing. We could get like the full command line, but you can see it's just OXDF, so nothing interesting there. PS scan, PS tree, different ways to look at processes, and that's kind of basically that we get like a net stat kind of thing. So let's take a look at linux.pagecache.files and see what kind of files we can get access to. And this is going to dump a ton of stuff. And I wonder if there's a way to make it a little smaller so that it has smaller text, but we fit it on one line. What is happening? Not really. Well, kind of, no. There's a ton of stuff here. We want to look kind of down here at the end is the file name itself, files we have access to. If we scroll up, we can, in fact, let's just do this. The file, I mean, really the file we're interested in, at least to start, is oxdf.bin, or /bin/oxdf. I'm gonna make this bigger again because we can, now that we're grepping. And, oh, that was a mistake. Sorry, now we gotta fix it. Now we gotta fix this. Let's go here, let's go to the top, and that looks better. Let's go up, there we go. Okay, so we do have bin oxdf, it's in files. There's a cool, so we can do -help on this. There's not a lot of options here. We can find, if we do -find bin oxdf, it'll return just that, but that's not super useful. We want to go to the page cache -recover fs. And if we do -h on this, we can see not a lot there, but let's go ahead and do this. It's going to recover into a compressed tarball. So if we run this, it's dumping all the files here, and we run ls, and we now have recovered fs.tar.gc. We can do tar-tf recovered, and it will print the files we have access to now. And oops, went too far. So nothing super interesting. So we have an ash history file here. We have /bin oxdf. We got our standard stuff. That looks like basically it. So let's make dir recovered files, move recovered. What is this? FSR to let's try. I think it's tar minus xf minus c recovered files. I hope this works. Recovered. I need to be after the F here. Recovered FS. I think that'll work. Oops. Let's see. So ls recovered files. Yeah. Okay. Sweet. So if we go into recovered files, find dot minus type f cat 11 dot hash history. So we've got netcat running here. We've got some. We're running oxdf here. Nothing super exciting. Let's do file on that bin oxdf, and boom, we have a Linux executable, not stripped. So I will open up a new window, open up Ghidra. We are going to need to take a look at this. Rainbow here. Let's make a new project, non-shared. Location will be bam, bam, bam. Where's my Uncheesable? I like to just make a Ghidra directory, select directory. Name will be uncheese, and we'll finish. We will import file to cheesable covered files. We're in the 11 bin oxdf. Linux executable. Let's take a look. And we will open it, see what we can get here. Yes, I'd like to analyze it. You can see down here the progress. It is making pretty good. Let's see, it's working through, and it is done. We'll go to functions, and might as well start. There's a bunch called dummy, connect, close, exit, entry. 3 functions that are fun. Only 3. This is a small binary. So main seems a good place to start. All right, let's see what's going on here. I'm not going to spend a ton of time really cleaning this up because I don't. This right here is basically the whole thing, and we can sort of real quickly just sort of figure out what's happening. So when we see like H to network short and H host to network long, these are taking these numbers and converting them to network byte order. We have an SA family, and then we're defining here a struct. This is how we define a socket. So we're gonna have a family here. We can real quickly set equate, and I think this is inet, right? Yeah. I think that's right. So we can set that there. This is gonna be the port number, and this is gonna be 10. I can just tell you right now from like this is the IP address, and it's 4 bytes. The first byte is A0 or is A, sorry, and A is 10. Then we have 000202. So this is basically creating a connection to port OX1111, which we can make as 4369 on 10022. It's going to create that socket. It's going to connect to that socket. And then let's keep going down. Now we have, so let's see, we'll call this rename variable socket fd. This is what's going to rename this variable res for like result. As long as the socket connection works, it's not. If it doesn't work, it exits. Now we're going to have md. We have to change this name because so we're going to call mfd create on something called oxdf. And so if we look at mfd create, it's just calling the syscall 13f. If we let's see, where is this? Linux syscall. Chromium has always a good table. Scroll down to find OX13F. Was that right? Yep, MFD create. Now we're going to come back to this in a little bit more detail, but there is a really this is what this is doing. If we look at MFD create, can I click here? Now let's grab this. Google is going to create an anonymous file. So this is going to create like an in-memory file. So it's like the program can treat it like a file, but it only lives in memory, and so it's not going to create stuff on disk. So we've got that system call. So, and param2 is going to be the size, I believe. No, not the size, the name. So we are going to create something called, we're going to create something basically called OXDF right here. It's a temporary file. So we'll call this rename variable temp file fd. Cool. Then we're going to, while true, we're going to read off the socket up to 400 bytes into local 418, and then we're going to write local 418 into the file descriptor 400 bytes. And as soon as that read fails, we're going to break. We're going to set the memory of this thing to 0. We're going to close the socket, and then we're going to exec whatever's there and run it. So the question really is, what is in that file? Like, what is in that file? And I don't have access to 10.0.0.2, so I basically have to figure out, can I recover this file from memory? So let's go back here. I'm going to come back here and go back to our volatility. Let's see. Oh, maybe we'll just go to a new one and do vol -f mem there -s symbols. And now we need a plugin. We want to see about the file. So how can we do that? We will go back here. We'll see if we can find our I guess I could just run it again, but our help, here we go. There is one I kind of skipped over earlier, but LSOF lists the open files for each process. So that is exactly what we want right now. So we'll run that plugin. I probably should have given it a thing because it's going to run. Let's run this again. I see what I need right now, actually, but let's run it with help. We can give it a PID 64 like that. And now it'll just show us the OXDF process. If we did, was it 52, I think? I think it was 52 that was the bin process. I bet it will have, it just says dev console. Okay, unimportant. Let's go back to 64 and get the OXDF process. So we have standard in, standard out, standard error. We have the socket right here, it's getting FD, and we have memfd OXDF deleted. So there is a file there that we can, it is still there and being held open by the process at the time that this was run, which means we have a chance of getting access to it. There's a really nice blog post, and I've got a reference to it somewhere. Let me see if I can find it. And this is actually a blog post by Canopus on his blog. So this is going over fake door. I think this was recently just published. Oh yeah, this was just published a week ago. And there's a lot going on here, but this is about a malware dropper that is using this temporary file system. What was why am I blanking? Where am I losing the memfd create? That's what I'm looking for. Memfd create. Boom. So in this one, you've got some code that creates a wrapper here, and then it reads off a socket into it. This is looking very familiar, and then it executes it. So it sleeps for some time and executes it just like ours does. And so skipping ahead to this part of the thing, let's see. Maybe I need to keep going. Memfd create. Scrolls down. Let's see. So how do we find this in memory? We need to go into vol shell. And so vol shell is like a way of interacting with almost like a Python system here. So if we go into vol shell, I need to give it the mem.elf. I need to give it symbols, and I need to give it -L so it knows to go into a Linux shell. Otherwise, it'll not behave the same. First, we need to find the process. So we can do git process. So actually, we can start with just running help. So we run like that. Yep, like that. And it will show us all the different things the commands we can run. So like GP is short for get process or get task. Display type shows stuff about, shows like information about an object. We'll use both of those. There's a lot in here. But so if we want to do get process, PID equals 64. PID equals 64, that's better. So we can say proc is equal to, and we're just now, so now we have proc is here. We can do DT on proc, and it will show us all the information about it. Can I make this big enough that I get on one line? Yeah, there we go. If my head is over you over here, sorry about that. I think I'm good. So we have all this information about the proc here. Now in here, let's see, there is a files. Hopefully, I think there is. We can search for it if I don't see it. Oh, here, files object right here. So this is a struct that defines the files that are opened by the process. And so we can actually do .files here and actually get information about, so here's the files, the table, and then some data here. This is a little tricky, but I'm pulling this off of the Canopus thing. We can say, so we'll say from volatility till it free.framework.symbols import Linux. And then we can do linux utilities file descriptors for process self.context self.current symbol table. And I'm just getting all this out of the blog post. Proc. Give it our process like that. And we'll say, we'll name this like fd generator is equal to that. And so now we can say for fd in fd gen print fd. Is that gonna work? Yeah. Okay. So cool. So we can see standard in, standard out, and standard error are all pointing at the console. And then we have our socket, and then we have our file here. And this right here is our offset to the file within the dump. So now what we need to do is we need to get a hold of that. So we can say file is equal to self.context text object type. Again, pulling this from this blog post, self.current symbol table bang file. Type all that right will be awesome. Layer name is equal to layer name. I don't totally understand why we do this, but he does go into the blog post as to why. And then offset is equal to u. We close that, and we presumably have file. So we can do dt on file, and boom. Now we have all this information about the file, including, if we scroll down here somewhere, here right here is in the struct at offset A8 is the inode value. So I'm going to grab that, and I'm going to drop out of the shell. Because now we can do vol -f mem.elf s symbols linux.page cache.inode pages. I'll show you this one has a help. If we pass it, so this is going to list and recover cache pages. So if we pass it -- inode and the number, and then the -- dump, going to run and try to pull that file. And if we look now, we have inode boom.dump. If we run a file on this, it is another elf executable. If we try running it, change mod plus x inode, it prints a flag for us. So that was the challenge. That is very similar to, scroll down here. We do the same thing here where we get the inode, we dump it, and then we say boom, boom. This is an XOR, so it's slightly different, but same kind of thing. We can dump it. So this took me a lot longer than it probably looks in this video. This was very challenging. Thank you so much to Canopus for making this. I love that you know so much about this stuff. I love that you're putting it out there and trying to share it and teach people. That's what this is all about. And thanks for taking the time to make it for me. This is the fourth of the 4 challenges in my CTF. Hopefully y'all enjoyed watching these, and I will be back with some sort of content, hopefully sometime soon. Talk to you later. Bye.